let's unpack this. Today we're taking a truly deep dive into something that's, absolutely fundamental. It's the science that dictates safety in medicine, in public health, pretty much everywhere that matters. We're talking about microbial control.
Exactly. Sterilization and disinfection. And this isn't just about, wiping down a counter. It's a rigorous, hardcore science. And we have an excellent resource to guide us today.
We do. It's a really detailed one. We're leveraging the academic material Week 9 Sterilization and Disinfection, which was prepared by Dr. Mahmoud Abu Sheiba.
From the Microbiology and Immunology Department, Faculty of Medicine at Azzaytuna University in Libya. This document, it really sets the scientific baseline for anyone who needs to understand how we fight this unseen war against pathogens.
And the stakes are they couldn't be higher, right? Getting these principles right is the front line. It's how we prevent healthcare-associated infections, HAIs, which are, they're still a massive global problem.
A huge problem.
So our mission today is to really distill the technical stuff from this material, the specific agents, the methods, the temperatures, all of it into a clear, structured understanding.
Right, and that means moving beyond just the vague words people use, the confusion between, say, clean and sterile.
Yeah.
We need to get into the actual quantitative difference between them.
Precisely. We are establishing the definitive language of microbial safety.
So to start, we really have to get our heads around the idea that getting rid of microbes it's not a simple on or off switch. It's a spectrum. And it's a spectrum that we define mathematically.
Okay, so you're talking about how many of the microbes you actually manage to kill off.
Exactly. And the concept is called log reduction.
Log reduction. Now, for someone who isn't a microbiologist, why use a logarithmic scale? Why not just say, we killed 99%?
Because in a critical setting, like surgery, 99% is, it's nowhere near good enough. Not even close. The log reduction scale gives us the precision we need when you're dealing with potentially billions of microbes.
Right.
So let's start at the very bottom of that scale, the foundation. Cleaning. The technical term is decontamination.
This is the part you can actually see, wiping away the grime.
It is. It's the mechanical removal of the pathogenic microbial population. You're using soap, water, detergents to get rid of physical debris, organic matter. And this step, it absolutely has to come first. Always.
And what's the quantitative result here in terms of log reduction?
It's modest, but it's essential. You're looking at a reduction of at least log 1.
Okay, log 1. So that's a 90% reduction in what you call colony-forming units, or CFUs. If I start with 100 microbes, I'm down to 10.
Exactly. And the outcome of that is that the items are now considered safe to handle without protective gear. It's the prerequisite for everything else that follows.
Got it.
Now, moving just a little bit up the ladder, the source-defined sanitizing, which is, a bit simpler. It's just a process that reduces germs to a safe level. You hear this term a lot in, say, the food service industry.
Right. But now we get to the serious stuff, disinfecting. This is where we actually start talking about killing power.
This is a big jump. Disinfection is the process of killing most, if not all, pathogenic organisms. And the outcome here is quantifiable at a much higher level. We're talking a greater than or equal to 10 to the third log CFU reduction.
A log 3 reduction, 99.9%. So if you started with 1 million microbes, you're down to 1,000.
A huge leap from log 1, yes. But the really crucial distinction here for disinfectants is that they may not destroy bacterial spores. That's key. And they're generally toxic to human tissue, which is why they're almost always used on inanimate objects.
That toxicity is the dividing line, then.
It is. But there's a critical exception within this category, which is antiseptics.
Okay.
An antiseptic is basically a type of disinfectant that is safe enough to be applied to living body surfaces, like your skin or mucous membranes. The process of using it is called asepsis.
So it achieves that same log 3 reduction, but without, being toxic to us, which is why they're essential for prepping for surgery or cleaning a wound.
Exactly. And that brings us to the very top, the absolute pinnacle of microbial control, sterilization. This is the absolute non-negotiable standard for patient safety in any kind of invasive procedure.
Okay, so define definitive process for us.
Sterilization is the elimination or the complete removal of all living microorganisms. And that includes every single bacterial spore from an item or a medium. When we talk log reduction here, we were demanding a reduction of greater than or equal to 10 to the 6th log CFU.
Log 6. 6 nines of kill power. 99.999%. Okay, but wait a minute. You just mentioned that high-level disinfectants like glutaraldehyde can kill spores. So why do we need the complexity of a log-6 sterilant like an autoclave? What is that tiny extra fraction of a percentage actually protecting us from in a hospital?
That's a great question. And that extra, 0.0000001%, it's everything. When we say log 6, we are targeting a statistical point where there is less than a 1 in a million chance that a single viable spore remains on that instrument.
1 in a million.
Right. High-level disinfectants, while they are sporicidal, they don't guarantee that level of certainty, especially if the contact time is a little off or the concentration isn't perfect. Sterilization is all about maximizing the probability of safety to an almost absolute degree.
Because even one spore left behind could be catastrophic.
One spore of Clostridium tetani left on a surgical scalpel is a deadly, catastrophic failure. So that level of certainty for anything that's going to be implanted or that penetrates sterile tissue, it's completely non-negotiable.
That quantitative measure, log 6, suddenly makes a lot more sense, especially when you consider how incredibly resilient different microbes are. I mean, you can't just use the same chemical on every target because, well, they're not all created equal, are they?
Not at all. Microorganisms have evolved these incredible defenses. So we establish a very clear hierarchy of resistance. This dictates the strength and the method you have to use, moving from the things that are almost indestructible down to the most vulnerable.
Okay, so who's at the top of this list? What's the toughest thing to kill?
Well, number one is so far outside the realm of normal sterilization, it needs its own category. We have to start with prions.
The misfolded proteins?
Yes. They're not technically even alive. They're non-traditional infectious agents, but they are by far the most challenging entity to inactivate. Their structural stability is just immense. They're largely unaffected by standard sterilization temperatures.
So what do you do?
In neurological surgery settings where they're a risk, you're looking at harsh chemical destruction or extreme heat treatment, sometimes even incineration. Their resistance dictates some of the most robust, non-standard protocols in all of medicine.
Wow. Okay, so after the nearly unkillable prions, what's next?
Next is the primary target of any true sterilization process, the endospores of bacteria.
Right.
These are the dormant, metabolically inactive structures. They're protected by multiple, really tough coats. If your method does not kill the spore, it is not sterilization. Simple as that. This is literally why the autoclave was invented.
Moving down the list, who has special defenses that we need to worry about?
Next up are Mycobacterium species. So the organism that causes tuberculosis, they have this high concentration of waxy lipids, mycolic acids in their cell walls, and that just repels many common chemical agents.
So they're way harder to kill than your average bacteria.
Oh, much harder.
Right.
Which is why they're high up on the target list for intermediate to high-level disinfection. Below them, we find multicellular pathogens, the cysts of protozoa, followed by their less resistant form, the vegetative protozoa.
And how do the more common bacteria that we hear about all the time stack up?
Well, we look at their gram-stain characteristics. Gram-negative bacteria are next. They're generally harder to kill than gram-positive bacteria because they have this complex outer membrane layer. It acts like a barrier against a lot of disinfectants.
Okay, and then
Then come fungi, and that includes most of their spore forms.
now viruses. This is fascinating to me because they're split into two very distinct groups on this resistance list.
It really is. And the difference is basically like a tough shell versus a fragile bubble. You have naked viruses. Those are the ones without a protective lipid envelope.
Like poliovirus or rotavirus.
Exactly. They're tougher because their protein coat, the capsid, is very stable, and it requires a stronger chemical to break it down. So they're actually more resistant than a lot of bacteria.
And then at the very bottom of the list, we find the least resistant organisms.
The easiest to kill. First, gram-positive bacteria, which don't have that protective outer membrane their gram-negative cousins have. And right at the very bottom, the envelope viruses.
So things like HIV, SARS-CoV-2, influenza.
Yes. They are surrounded by this fragile lipid envelope that they steal from the host cell. And lipids are just, they're so easy to dissolve. Soap, alcohol, many low-level disinfectants just pop that bubble, making them the easiest category of pathogen to inactivate.
So understanding this whole hierarchy lets you choose the right weapon for the job without, going overboard and damaging instruments or using something unnecessarily toxic.
That is the entire point. It's about appropriate use of force.
That resistance hierarchy is the map then. So now we need to define the arsenal. We can categorize disinfectants into 3 levels based on what they can kill, which gives us a practical framework for how to use them.
Right, and their ability to kill is defined entirely by their success against those tough targets we just listed.
Okay, let's start at the top. High-level disinfectants, or HLDs.
HLDs are the real workhorses for what we call semi-critical instruments. So things that touch mucous membranes or non-intact skin, but can't be put through a heat sterilizer.
So what's their definitive kill profile? What's on their hit list?
They destroy all vegetative bacteria, all fungi, and all viruses, both the enveloped and the naked ones. And crucially, they kill tubercle bacilli,
The mycobacteria?
the mycobacterium that gives other chemicals so much trouble. Now, their action against bacterial spores is listed as plus or minus in the source,
Meaning?
meaning they are sporicidal when they're used correctly. You often need really long contact times, but they lack that absolute 1 in a million log 6 guarantee is sterilization.
But the fact that they handle tubercle bacilli is a big deal. It means they can get past that waxy cell barrier that stops the intermediate level agents.
Absolutely. And as you look at the chemicals that can actually do this, you see the high potency agents. You've got the aldehydes, glutaraldehyde and OPA, parasitic acid, and concentrated hydrogen peroxide.
These are highly effective.
Very. But they often come with high toxicity, or they're corrosive, which is always the trade-off you make for that kind of killing power.
Okay, so moving down a level, intermediate level disinfectants, or ILDs, this is where the spore-killing reliability really ends, right?
This is the definitive boundary line. ILDs destroy all vegetative microorganisms. So gram-negative, gram-positive bacteria, most fungi, all viruses.
Yeah.
But they have no action on bacterial spores. None.
Which makes them suitable for non-critical items, or say, environmental surfaces where you're not really worried about spores.
Exactly. But their key utility is that they are effective against tubercle bacilli.
Right.
So you need them for surfaces that might be contaminated with bodily fluids, or for instruments that only touch intact skin. And it's interesting, the physical methods listed in this category, pasteurization, boiling, steaming, they all fail against spores, which confirms their ILD status.
And the chemical agents here are the ones we see all the time.
Oh yeah, they're extremely common. You have alcohols like 70% ethyl and isopropyl. They're rapid killers, but they evaporate really quickly. Then you have phenolics, lysol, cresol.
And those are prized because they work even when there's organic gunk around.
Right, they retain their activity in the presence of organic matter, which is a huge advantage. And finally, you have the halogens like iodine and chlorine. They often fall into this category depending on the concentration. It's a balance of efficacy, cost, and toxicity.
Okay, last one. Low-level disinfectants, LLDs. The lowest rung on the ladder.
These are your housekeeping chemicals. For routine surface cleaning, where the risk of transmitting really tough organisms is minimal.
So what can they kill?
They only destroy the easiest targets, vegetative bacteria and the enveloped viruses. Crucially, they have no action on bacterial spores or on tubercle bacilli. Their activity against the tougher, non-enveloped viruses, like norovirus.
Which causes those horrible outbreaks.
Exactly. Their activity against those and fungi is only variable. It's a plus or minus.
So if there's any risk of mycobacterium or a spore former, an LLD is a dangerously wrong choice.
It's a guaranteed failure. The chemicals here are things like quaternary ammonium compounds or QACs and chlorhexidine. They're generally safer and less toxic, which is why they're so common in general cleaning products.
But there's a catch.
A big one. QACs in particular are extremely sensitive to being inactivated by organic matter. So you absolutely must pre-clean meticulously for them to work at all. The lower toxicity in this case correlates directly with lower killing power.
Right. So moving from chemistry to physics, physical methods are often the most reliable way to get to that log 6 certainty. We're talking about forces like heat, pressure, filtration, and energy.
Yes, and these methods tend to remove some of the variable human element that you get with mixing chemicals and timing contact. They offer quantifiable guarantees, especially with heat.
Heat is the big one, but we need to understand the precise difference in how dry heat and moist heat actually work.
That's the key.
So why is moist heat considered so much better for sterilization?
Well, dry heat kills primarily through oxidation, denaturation, and just straight-up charring. It takes a lot of time and very high temperatures. We're talking 160 degrees Celsius for 2 hours.
It's like baking something until its structure is just destroyed.
That's a great analogy. Moist heat, on the other hand, kills by the rapid denaturation and coagulation of the cellular proteins. And that process requires significantly less energy and less time.
And the deep science here is about latent heat transfer, isn't it?
Yes, this is where it gets really cool. Saturated steam, which is what an autoclave uses, carries a vast amount of what we call latent heat. When that steam hits a cooler object, it immediately condenses back into water. And in that moment, it releases this enormous amount of energy instantly.
Massive energy dump.
A massive energy dump. And that heat energy penetrates and coagulates proteins so much faster than hot, dry air ever could. That rapid transfer of latent heat is the reason why moist heat at 121 degrees Celsius kills in 15 minutes, but dry heat at 160 degrees takes 2 full hours.
Incredible. So just to review the dry heat conditions, 160 C for 2 hours, and that's good for glassware, oils, powders, things that steam would damage. And the control indicator is tough spores like Clostridium tetani or Bacillus subtilis.
Correct. Now let's explore the categories of moist heat that happen below the normal boiling point of 100 degrees Celsius.
Okay.
First, we have pasteurization. This is a crucial ILD for heat-sensitive liquids like milk and juice. The goal is to make it safe while preserving the flavor.
Right, there's the Holder method and the flash method.
Yes, Holder is 63 degrees for 30 minutes, and flash is a hotter, shorter 72 degrees for 20 seconds. Both kill non-sporing pathogens, but we did note that the really hardy bug Coxiella burnetii might actually survive the gentler Holder method, which just shows you its limits.
And what about gentle heating for really specialized lab media?
That's called inspissation, or fractional sterilization. This involves heating something on 3 successive days at a relatively low 80 to 85 degrees Celsius.
How do I do that?
These are for complex media that are rich in egg or serum, like algae medium for TB culture. If you put on a standard autoclave, it would instantly coagulate into a useless rubbery mess. So we use this gentle, multi-day approach to disinfect the media while keeping it functional.
Okay, so what about moist heat right at 100 degrees Celsius?
Well, you've got simple boiling. Boiling for 15 minutes is an effective intermediate level disinfection. Same with simple steaming at 100 degrees for 90 minutes, but both of them fail against spores.
But you can adapt that multi-day approach we just talked about to get around the spore problem, can't you?
You can, and that method is called tyndallization, or intermittent sterilization.
This is the really clever part. So explain why steaming at 100 degrees for just 20 minutes, but over 3 consecutive days, suddenly does kill the spores when a single 90-minute blast won't.
The trick is the incubation period in between the heating cycles. The first heating kills all the active vegetative cells, but the spores survive.
Right.
So then you let it sit in the nutrient-rich media like gelatin or sugar solutions at room temperature overnight. This cool-down period allows the surviving spores to germinate. They wake up and turn into metabolically active, heat-susceptible vegetative cells.
And then you zap them.
Then you zap them on day 2, and again on day 3 to catch any late bloomers. You're overcoming the spore's main defense without using destructive high heat.
That allowance for germination, that's the key insight. But tyndallization takes days. If you want instantaneous sterilization, you have to use pressure. You have to use the autoclave.
The autoclave is the gold standard of moist heat. It achieves temperatures above 100 degrees Celsius by increasing the pressure. The industry standard is 121 degrees Celsius for 15 minutes at 15 psi.
And this is for everything: instruments, gowns, culture media, contaminated waste.
Everything that can take the heat and steam. And the ultimate safety check, the biological indicator we use to validate it, is a vial of spores from Geobacillus styrothermophilus. If you can kill those, you can kill anything.
So the log 6 concept applies directly here. How does something called the D value tie into the autoclave's timing?
The D value. That's the decimal reduction time. It's the time requires a specific temperature to kill 90%, or 1 log, of a microbial population. So for the autoclave, we use the D value of those G. styrothermophilus spores. The process has to be long enough to achieve at least 12 D values of kill for those incredibly tough spores.
Yeah.
That's what statistically guarantees sterility. So when we say 15 minutes at 121 degrees, that time is mathematically calculated to blow way past the log 6 threshold for the toughest target imaginable.
So when heat just isn't an option, we have to turn to filtration.
Right. And filtration is not a process of killing. It's a mechanical process of removal.
And this is absolutely essential for those heat labile liquids. Vaccines, antibiotics, toxins, sugar solutions, things where heat would just destroy the active components.
And for that, we rely on membrane filters. The most important number you need to know in bacterial filtration is the pore size, 0.22 micrometers.
0.22. Why that specific size? Why is that the universal industry standard?
It's the standard because it reliably stops all known bacteria and bacterial spores. The critical pathogenic bacteria, even notoriously small and motile ones like Pseudomonas aeruginosa, are larger than 0.3 micrometers. A 0.22 micrometer filter gives you that margin of safety to retain all of them, producing a sterile filtrate.
But as you pointed out earlier, it's not a guarantee against the very smallest viruses.
Correct. The smallest viruses are often measured in nanometers, like 20 nanometers, and they can absolutely pass through a 0.22 micrometer filter.
And what about filtering air?
For air purification, we use incredibly effective filters. HEPA filters remove 99.97% of particles that are zero point 0.3 micrometers or larger, and ULPA filters push that even further to 99.999% of particles 0.12 micrometers or larger.
These are the hidden heroes in biosafety cabinets and operating rooms.
They are. They are constantly maintaining the sterility of the environment.
Our final physical method is pure energy. Let's start with ionizing radiation, which is often called cold sterilization.
Ionizing radiation, so X-rays, gamma rays, from a cobalt-60 source, it works by just smashing into DNA and causing irreparable double-strand breaks. And it does this without any increase in temperature.
Which is a huge advantage.
It's a massive advantage. That high penetrating power and the lack of heat makes it perfect for sterilizing prepackaged, single-use, disposable medical plastics. Things like syringes, catheters, prepackaged tissue grafts.
It sounds ideal. Are there any limitations?
Well, it's very expensive. It requires heavy shielding to be safe. And interestingly, the source material notes that it is not effective against certain viruses.
Yeah.
The control we use to verify the dose has been delivered correctly is Bacillus pimelus.
In contrast, non-ionizing radiation UV light is, it's everywhere. But its practical use is pretty limited.
Extremely limited. UV is quite lethal to microbes, but its major drawback is its poor penetration. A thin layer of dust, a piece of glass, even water will block it immediately.
So it's only good for line-of-sight sterilization.
Exactly. You need a specific wavelength, 250 to 300 nanometers, for about 30 minutes. It's used for sterilizing the air and clean surfaces in places like operating theaters and laminar flow hoods, where you need to maintain sterility. But it can never sterilize, say, an instrument that's inside a sealed package.
Okay, so having mapped out the entire physical arsenal, let's pivot to the chemical solutions. These are the agents we rely on when heat is impossible or when we just need a fast-acting topical solution.
Right, our chemical toolkit.
Let's start with a foundational one, alcohols.
Alcohols, specifically 70% ethyl and isopropyl alcohol, are fundamental. They kill by denaturing proteins and by dissolving the crucial lipid membranes of microbes.
And that mechanism, dissolving lipids, explains why they're so good against enveloped viruses like the flu or HIV.
Precisely. They're fast-acting against bacteria and most fungi, but, and this is a big but, they are definitively not sporicidal.
And there's that weird quirk about the concentration, right?
Yes, they're often most effective at 70% concentration, not 100%. The remaining 30% water is actually necessary to help the alcohol penetrate the cell and facilitate the protein denaturation process. 100% alcohol just dehydrates the microbe, which can actually preserve it.
Okay, now we move into the realm of true chemical sterilants, the aldehydes. These are the heavy lifters of non-heat sterilization.
They absolutely are. They are sporicidal because they are highly reactive agents. They combine with and permanently inactivate proteins and nucleic acids through processes called alkylation and cross-linking.
The classic example is formaldehyde.
Formaldehyde is highly effective, used for fumigation and preserving anatomical specimens. But its toxicity, its corrosiveness, its strong irritation, it requires very specialized, careful handling.
So the major replacement for many applications was glutaraldehyde, often sold as 2% Cydex. That's used for delicate instruments like endoscopes.
Right. Glutaraldehyde is less toxic than formaldehyde, which made it the standard for sterilizing these heat-sensitive scopes for a long time. It's used at a 2% concentration for about 20 minutes for high-level disinfection, or for much longer for full sterilization.
But even glutaraldehyde has its own operational challenges.
It does. It requires careful activation before you can use it, and its vapor is an irritant. And that's why orthophlaldehyde, or OPA, has become such a major industry advancement.
Okay, so OPA is used for the same thing, endoscopes, cystoscopes, but it offers some significant wins in a hospital setting.
Huge wins. Let's focus on those. The fact that OPA does not require activation is a massive operational benefit. In a busy hospital, that eliminates a huge potential failure point that comes from staff having to correctly mix chemicals under pressure.
Makes sense.
It also has a better odor, low vapor properties, it's more stable, and critically, it shows increased mycobactericidal activity compared to glutaraldehyde, so it's even better at tackling those tuberculosis risks.
The trade-off is probably cost.
The trade-off is often cost, yes, but the safety and efficacy gains are really significant.
Okay, next up, phenolic compounds. You said these are crucial because they solve one of the biggest problems in disinfection.
They do. They solve the problem of organic matter.
So what's the specific mechanism that lets them keep working when other things fail in the presence of, blood or pus?
Phenolics kill by damaging the cell wall and the membrane structures. And unlike hypochlorites or QACs, their chemical structure resists interference from the proteins and lipids that you find in organic soil. They retain their activity in the presence of organic matter.
Which makes them the go-to choice for general surface cleaning in clinical areas that get frequently soiled.
It does. The highly toxic varieties like Cresol and Lysol are disinfectants, while the less irritant derivatives are common antiseptics. This includes chlorhexidine, which is the active ingredient in Savlon, and chloroxylenol, which is the active ingredient in Dettol.
It's pretty amazing that two of our most relied on agents, iodine and chlorine, basically kill through sheer brute force oxidation, just tearing the microbe apart.
They're incredibly powerful oxidizers. Iodine is the traditional skin antiseptic. It kills by oxidizing cellular components and iodinating proteins. Iodophores like betadine are just modern, more stable versions that are less irritating than a simple iodine solution.
And chlorine, in the form of sodium hypochlorite or bleach, is the undisputed champion of widespread, low-cost disinfection.
It is the most commonly used disinfectant on the planet. It's essential for water safety, in our drinking water, in swimming pools, and for large-scale industrial disinfection in the dairy and food industries. Its big drawback, which we'll get into, is its extreme sensitivity to organic matter and its rapid instability.
Moving on to other oxidizing agents, these are our non-halogen chemical sterilants, and they work by creating highly aggressive free radicals.
Yes, the hydroxyl radical.
Output.
Hydrogen peroxide, H2O2, is a chemical sterilant when it's used at a high enough concentration. You need about 10% for spores and for organisms that produce catalase, which is an enzyme that breaks it down easily.
And it attacks everything.
Everything. DNA, lipids, membranes. But its major advantage is its clean breakdown.
Right, it just turns into water and oxygen.
Exactly. That makes it environmentally safe and leaves no toxic residue. This is why it's ideal for disinfecting things like ventilators, soft contact lenses, and tonometer biprisms. And the vaporized form is absolutely crucial in low-temperature plasma sterilization.
Plasma sterilization, that's the really high-tech solution for delicate instruments.
It is. It's a low-temperature process below 50 degrees Celsius. You use a vacuum and energy to create a plasma from hydrogen peroxide. The active killing agents are UV photons and those highly reactive radicals. It avoids the heat damage of an autoclave while still getting you that log-6 certainty for very expensive, very delicate surgical tools.
Let's touch on heavy metal salts. They seem more historical than current practice.
They are, for the most part. They're relegated to very specialized uses today. They kill by combining with protein groups, specifically sulfhydryl groups, and that inactivates or precipitates the proteins. They're often bacteriostatic, so they just inhibit growth rather than outright killing.
But what are the current essential uses that are still around?
Well, silver sulfatazine is still absolutely essential for topical use on binds. A 1% silver nitrate solution is used in the eyes of newborns to prevent ophthalmia neonatorum. And copper sulfate is a standard fungicide and algicide for large bodies of water.
And mercury.
Mercury salts like thiamersal are really only retained now as a preservative in some vaccines and sterile.
Okay, finally, the chemical method that combines high penetration with low temperature, gaseous sterilization with ethylene oxide, or ETO.
ETO is the gaseous answer for heat-sensitive items that just can't tolerate liquid chemicals.
And how does it work?
A powerful alkylating agent, so it achieves log-6 sterility by reacting irreversibly with cell proteins. Its huge advantage is its incredible penetrating power. It can get deep into complex instruments and even through plastic packaging.
But the drawbacks are immense. It sounds like it demands extreme caution.
Oh, absolutely. ETO is highly volatile, it's flammable, explosive, and irritant, and crucially, it's a known carcinogen. Its use is incredibly heavily regulated. Because it's so hazardous, it's supplied mixed with air gases. The process itself is very slow. You're looking at 5 to 8 hours at 38 degrees Celsius or 3 to 4 hours at 54 degrees. And after that, it requires extensive aeration to remove the toxic residues.
So it's only reserved for high-value items that have literally no other sterilization option.
That's right. Disposable plastic petri dishes, heart-lung machines, synthetic sutures, complex catheters, intricate dental equipment. The control used to verify this long, dangerous process is Bacillus globigii.
We've established the perfect method and the perfect agent. But in the real world, a perfect protocol can fail because of the environment or the circumstances. This next section, the factors affecting efficacy, this feels vital because this is the difference between a theoretical kill and practical patient safety.
You're absolutely right. A failed sterilization cycle is often a function of the environment, not a deficiency in the agent itself. And there are 9 critical variables that practitioners have to manage constantly.
Let's start with the most basic one, the sheer numbers, organism load.
The more microbes you start with, the longer it takes to achieve that log 6 reduction. It's simple math. If you have 10 to the 9 CFUs, you need 3 extra D values of kill time compared to if you started with 10 to the 6.
Which is why cleaning must always precede sterilization.
It's the mathematical certainty behind it. If a highly soiled instrument goes into an autoclave, the standard 15-minute cycle, which was calculated for a lower load, might not be sufficient to kill the vastly greater initial number of microbes.
And the nature of organisms. This relates directly back to our resistance hierarchy.
It does. If you unexpectedly encounter a prion, your standard 121-degree autoclave cycle is going to fail. If you suspect Mycobacterium, you have to use an intermediate-level disinfectant or higher. You must always choose a method that targets the toughest pathogen you anticipate facing.
Concentration and temperature seem pretty straightforward, but you mentioned a counterintuitive point about heat earlier.
Yes. Generally, higher concentration and higher temperature increase the kill rate. That's true. However, pushing the temperature too high can actually degrade or inactivate certain chemical agents.
So more heat isn't always better.
Not always. For instance, some disinfectants will chemically break down above a certain point, which renders them useless. Even though the heat by itself might be killing some microbes, you have to operate within the agent's specific stability window.
And what about the stability of the agent itself, just sitting on the shelf?
Stability is such a hidden failure point.
Mm-hmm.
Hypochlorite solutions bleach are notoriously unstable. They degrade rapidly, especially once they're diluted or exposed to light. They lose their potency so quickly.
So if a hospital staff member is using a bleach solution that was mixed yesterday,
They might just be applying slightly salty water, not a disinfectant. That's why fresh, daily preparation is often a mandatory protocol.
okay, we've mentioned the obvious variables like contact time, where more time equals better kill. But how does something like relative humidity complicate sterilization?
Relative humidity is absolutely critical for gaseous disinfectants like ETO.
Ethylene oxide.
Right. ATO, as an alkylating agent, requires a specific level of hydration to work, usually between 30 and 50% relative humidity. If the environment is too dry, the bacterial spores remain dehydrated, and the ETO gas can't penetrate their coats to react chemically with their contents.
So if it's too dry, the gas just bounces off.
It fails completely. The process is a total waste of time and resources.
Now, for what might be the most common cause of failure in a real clinical setting, organic matter.
This is the absolute enemy of chemical efficacy. Organic substances, residual blood, tissue, pus on an instrument, can either physically shield the microbes from the disinfectant, or they can chemically react with the agent itself, rendering it inert.
Can you give us a practical failure scenario?
Absolutely. Imagine an endoscope had some residual protein material stuck inside a narrow channel. A powerful HLD like glutaraldehyde is pumped through. That protein coating physically shields the bacterial spores hiding underneath it.
So the chemical never even touches them.
And worse, the protein itself might chemically bind to and neutralize the glutaraldehyde before it even gets to the target. This residual protein completely defeats the sterilization process. This is a particular problem for hypochlorites and QACs.
Which gives phenolics and glutaraldehyde that massive advantage we talked about.
Exactly. They're the exceptions that can maintain their efficacy even when the environment is a little bit dirty. But the number one solution is, and always will be, meticulous mechanical cleaning before any disinfection or sterilization step.
Finally, the challenge posed by biofilm.
Biofilms are a nightmare. They are dense protective matrices that microbial communities secrete when they're stuck to a surface. They act like an impenetrable fortress.
But the disinfectant can't get in.
It can't get in. The biofilm prevents the entry and action of both disinfectants and sterilants. This requires aggressive mechanical action scrubbing with brushes or using specialized enzymatic cleaners to physically remove that film before the instrument can be safely treated with a chemical. You can't just rely on a sterilant alone to dissolve a mature biofilm.
With all these variables in play, from pH and stability to organic matter, we can't just assume a chemical agent works. We have to test its effectiveness, both in a controlled lab and under the chaotic reality of hospital use.
Exactly. And these tests represent the scientific community's evolving recognition that lab results rarely reflect real-world outcomes.
Let's start with the historical one, the phenol coefficient test or the Rydeal-Walker test. It sounds like it's fundamentally flawed for modern practice.
It is, but it was the starting point. Its purpose was simple. Measure the killing power of a test disinfectant against Salmonella typhi and compare that to the killing power of phenol or carbolic acid itself.
And if your disinfectant had a coefficient greater than 1, it was considered better than phenol.
Right, but it had two huge drawbacks. One, it only really evaluated other phenolic compounds accurately, and two, and this is the critical one, it was conducted without any organic matter present.
It simulated an unrealistically clean scenario.
Completely unrealistic. So a product that performed great in the Rydeal-Walker test might fail miserably in a real hospital in the presence of blood or pus.
So the Chick-Martin test sounds like it was a direct scientific response to that exact failure.
It's the next step in the evolution. It modifies the Rydeal-Walker protocol by incorporating the acting environment into the test. It forces the disinfectant to act in the presence of organic matter, like dried yeast or feces, to simulate a naturally dirty environment.
Which gives you a much more reliable measure of the disinfectant's true working capacity.
A much more reliable measure for what you'd encounter in a clinical or public health setting, yes.
Okay, so moving beyond just the initial kill rate, the capacity test, or Kelsey-Sykes test, focuses on the disinfectant's resilience over time.
This test answers a really key operational question. How long does this disinfectant maintain its activity when it's repeatedly challenged?
You mean like in a busy clinic?
Exactly. In a busy clinic, a soaking solution might be used for multiple instruments throughout the day. It's gradually accumulating microbial debris, it's getting diluted. The capacity test assesses the agent's ability to resist that degradation and retain its potency after it's been challenged again and again with microbes.
So you're making sure it doesn't fail midway through a busy shift.
That's the goal.
And then the ultimate check, the real-world acid test, is the in-use test.
This is the one that really matters. The Kelsey and Moore in-use test moves from the standardized lab to the actual clinical environment. It determines whether your chosen disinfectant is effective under the exact operational conditions of that facility.
So it's accounting for that hospital's specific water quality, the typical temperature, the staff's actual mixing protocols, the local germs.
Everything. It checks if the staff is using the chemical correctly, if the environmental factors are favorable, and if the chosen concentration is appropriate for the unique demands of that specific hospital ward. It is the final, practical validation that ensures the scientific theory translates into real patient safety outcomes.
We have covered an incredible amount of ground today.
We really have. We've completed an exhaustive exploration, moving from those foundational mathematical definitions of log reduction, all the way through the physical mechanisms of the autoclave and filtration, and finally to the specific chemical capabilities of aldehydes, halogens, and oxidizing agents.
Yeah, I think the most important takeaway for me is that successful microbial control really hinges on recognizing these necessary trade-offs. You're constantly having to balance speed of action against high toxicity or low cost against low stability.
That's the constant challenge. And the innovation in this field, from OPA replacing glutaraldehyde to low-temperature plasma sterilization, it's all driven by the immovable challenge posed by things like prions and endospores, which demand that guaranteed log-6 certainty.
The rigor that's demonstrated in the source material really highlights the crucial role these practices play in every aspect of health. I mean, every time you see a sterilized instrument pack in a hospital, you're looking at the successful result of complex physical and chemical engineering, all aimed at achieving a 99.9999% reduction of life.
That certainty is the absolute foundation of modern surgical safety and laboratory practice.
We really want to give a sincere acknowledgement and appreciation to the creator of this highly detailed and rigorously structured material, Dr. Mahmoud Abu Sheiba, and of course the entire Microbiology and Immunology Department, Faculty of Medicine at Azzaytuna University.
Their dedication to providing such comprehensive educational resources is just vital for current and future practitioners. It ensures that scientific diligence remains the bedrock of health security. We really commend the department and the university for their efforts in improving medical education and public awareness.
So what does this all mean? It means the next time you hear someone use the word clean, you'll know that sterile is 6 magnitudes of safety beyond it. And you now understand exactly what it takes to get there.